Hi students, welcome to my channel Thoughts of Physics.
So in the video series of current electricity, in this class I am explaining wheatstone's bridge and the balancing condition of wheatstone's bridge. So first, what is this wheatstone's bridge? So wheatstone's bridge, it is a network. So this wheatstone's bridge network consists of 4 resistors. Let us say R1, R2, R3, R4. You can say P, Q, R, S also, no problem. So here, I have taken R1, R2, R3, R4 or the 4 resistors connected in cyclic order in the form of a quadrilateral. So like this as shown in the figure. So the 4 resistors are connected in a cyclic order in the form of a quadrilateral. This is the Wheatstone's network. Now here, so a cell of EMF E is connected one pair of opposite corners. See here, see the point A and C. For these opposite points, a cell of EMF E is connected. That's why AC is called the battery arm. So AC is called a battery arm. A cell of EMF E is connected one pair of opposite corners. So AC is called battery arm because between these 2 points A and C, a cell is connected. So that's why AC is called battery arm. Next, for the remaining 2 opposite points, that B and D, is a galvanometer is connected. This is the galvanometer. The resistance of the galvanometer is G. So between the points B and D, galvanometer is connected. So that's why BD is called galvanometer arm. AC is called battery arm and BD is called galvanometer arm. So now this is called the Wheatstone's bridge network. Now here, if the resistances are adjusted such that the current through a galvanometer is 0. So if you adjust the resistances values R1, R2, R3, R4 such that the current through the galvanometer is 0, then the network is said to be balanced. So whenever the current through the galvanometer is 0, that means when the galvanometer shows null deflection or 0 deflection, then the bridge is said to be balanced. By adjusting the resistance values, we can make the bridge to balance, and when the bridge is balanced, the current through the galvanometer is 0 and the galvanometer show null deflection or 0 deflection. That is the condition for balancing condition of Wheatstone's bridge. That is the current through the galvanometer should be 0. That is the balancing condition generally. Now generally let us obtain the condition for balance in terms of resistances. So because we have to adjust the resistance values, so let us obtain the expression in case of resistances for the balance, condition for balance. Now for obtain the balancing condition, let us apply Kirchhoff's laws. Already we have studied in the last class Kirchhoff's first law and Kirchhoff's second law. So generally Kirchhoff's first law is applied at a point, that is node or junction. Kirchhoff's first law is applied at node or junction. So what is node or junction means? The point at which number of conductors meet, that is the node or junction. So Kirchhoff's first law is also called as Kirchhoff's current law. So this is KCL. So this KCL is applied at a point node or junction. So let us take the points B and D because the galvanometer current should be 0. So at point B and D, across these points the galvanometer is connected. So galvanometer arm is BD. Now let us apply the Kirchhoff's first law at the points B and D. So at point B here 3 conductors are meet. So those are here, this is the one conductor and this is another conductor and this is another conductor. So 3 conductors or 3 current elements are meet at point B. Now for these 3 conductors, let us apply Kirchhoff's first law. Already we have discussed the sign convention. The currents moving towards the junction taken as positive, the currents moving away from the junction taken as negative. This is the sign convention. Now at point B, here I1. So I1 is moving towards the junction. So I1 can be taken as plus. So plus I1. So just at the beginning, no need to mention plus. So it is I1. I1 means understood that it is plus I1. Next, it's over. Next, second conductor. So second conductor, the current is Ig. Ig is galvanometer current. So this Ig current, as you take this arrow mark, so it is away from the junction. So that's why this can be taken as minus Ig. Next, if you take the third conductor, the current is I3. So KCL, Kirchhoff's first law, is only applied for the currents. Now for the third one, I3 current, it is also moving away from the junction, that is minus I3. When it is moving away, minus I3 is equal to 0. This is okay, the equation if you apply the Kirchhoff's first law at the junction B. So that should be is equal to 0 because the algebraic sum of the currents meeting at the junction is equal to 0 according to Kirchhoff's first law. Now when the network is balanced, already we have seen the balancing condition. So when the network is balanced, already we have discussed that the current through the galvanometer is equal to 0. The current through the galvanometer is equal to 0. Now if you apply Ig is equal to 0 here, so from this equation I1, so minus I3 is equal to 0 because here Ig is equal to 0. That means if you take this minus I3 this side, it becomes I1 is equal to I3. When the bridge is balanced, this I1 is equal to I3. Actually here what happens means, when this network is connected to a cell, then what happens? This network draws some current from the cell. It is the discharging condition. Let us say some current I is drawn from the cell. Some current I is drawn from the cell. At point A is a point, that is the junction or node. At point A, generally this current divides into I1 and I2. The current I at point A, it divides into I1 and I2. Now at point B, what happens means this I1 current again it divides into Ig and I3. The I1 current at point B it divides into Ig and I3. At point D, what happens means this I2 and Ig both will add up. So I2 and Ig both will add up and it flows. I4 current flows. If you add I2 and Ig, that means I2 plus Ig is equal to I4. In this case, so Ig, what happens means here I1 current is divided, that is Ig into I3. At point C, okay, this is the node point. What happens means this I3 and I4 add and it finally it gives I current. Already we have discussed there is no accumulation of charge. The current entering the junction is equal to the current leaving. That is whatever the current I it is entering into the circuit, same current I it is coming out of the circuit. So this is what happens here. So we have to follow proper sign convention for this by seeing the arrow marks, how the currents are moving like this. We have to see. Now, so for applying B point, here we have taken that I1 it is moving towards plus, Ig it is moving away minus, I3 it is also moving away minus I3. The algebraic sum of the currents meeting at the junction is equal to 0. Balancing condition means Ig is equal to 0. Then we can say I1 minus I3 is equal to 0. So I1 is equal to I3. Now, so now B point we have applied the Kirchhoff's current law, that is Kirchhoff's first law. Similarly, let us apply the Kirchhoff's first law at the junction D, because between B and D we have connected the galvanometer. So it is the galvanometer arm. So when the current through the galvanometer is 0, then the bridge is said to be balanced. Now let us apply Kirchhoff's first law at the junction D. If you apply at the junction D, here at point D, again 3 conductors are meet. Those conductors are this one, which having the current I2, and the second one this one, which is having the current Ig, and the third one this one, which is having the current I4. The 3 elements meet at a point D. Meet means that may be moving towards or away, that is meeting. Now here, if you apply the sign convention here, so now this conductor, this is moving towards the D. I2 is moving towards the D. When the current is moving towards the D, we can take plus. So that is plus I2 here we have taken. Next IG. IG also moving towards the D. Arrow mark if you observe. So you should be very careful here while applying sign convention. You have to take the arrow marks like this only. Because here only it divides and added according to this arrow marks only. Now here IG arrow mark if you observe, it is moving towards the D, so that's why plus IG, and I4 if you observe that from D it is moving away, so that's why minus I4 is equal to 0. So the network is balanced. We are obtaining the expression for balancing condition, so that's why when the network is balanced, IG, the current through the galvanometer, is equal to 0. Then if you write Ig is equal to 0 in this expression, we will get I2 minus I4 is equal to 0. So if you take this I4 this side, it gives I2 is equal to I4. Let it be equation number 2. Equation number 1 is I1 is equal to I3 when bridge is balanced. I2 is equal to I4 when bridge is balanced. That means this I2 is equal to I4 and this I1 is equal to I3. Now we have applied Kirchhoff's first law at the junctions B and D. Now let us apply Kirchhoff's second law. Kirchhoff's second law. Generally, Kirchhoff's second law is applied for a closed loop or mesh. Kirchhoff's second law, that is Kirchhoff's voltage law. So is applied for a closed loop or for a mesh. Now let us consider a closed loop here. Closed loop means from where the point we have started, we have to end with that point only. Then it becomes a closed loop. Here I am taking a closed loop. So I have shown here also the closed loop. A, B, D, A. A, B, D, A is the closed loop. So now for closed loop we are moving from A to B, again from B to D, from D to A. Then we will get the closed loop. So let us move one by one, step by step, then apply the Kirchhoff's voltage law. Now before applying Kirchhoff's voltage law, let us recall the sign convention. So sign convention means as we are moving in the direction of current, IR product is taken as negative. When we move in the opposite direction of current, IR product is taken as positive. So let us apply that sign convention here. Now from A to B, A to B means we are moving in the direction of current. This is the direction of current. So from A to B means in the same direction of current we are moving. When we are moving in the same direction of current, IR product is taken as negative. So minus I1 R1. Current is I1, resistance here, that is R1. The product gives potential difference. So I1 R1. So that is minus I1 R1. We are applying Kirchhoff's voltage law for the loop A, B, D, A. A, B, D, A. So A, B, D, A means this is A, B, D, A. From A to B means we are moving in the same direction. So minus I1 R1. Next, from B to D. B to D means we are moving in the same direction of current. That current is IG. We are moving in the same direction of current means again the IR product is taken as negative. Here R means resistance. The resistance of the galvanometer is G. The product means IG into G. In the same direction from B to D means in the same direction. So same direction means minus. So minus IGG. So that is minus IGG. That is from B to D. Next from D to A. If you want to complete the closed loop, we have to move from D to A. So D to A, as we are moving in the opposite direction of electric current. See, arrow direction of electric current is from A to D, but we are moving from D to A in the opposite direction of electric current. So when we are moving in the opposite direction of electric current, the product of IR can be taken as positive. So IR product means I2 R2 is taken as positive. So that's why plus I2 R2, that is equal to 0. This is the equation. So we will get by applying Kirchhoff's second law for the loop ABDA. Now, so when the network is balanced, so the current through the galvanometer is 0. When the current through the galvanometer IC is 0, in this equation, if IC if you take 0, then it gives minus I1 R1 plus I2 R2 is equal to 0. Then if you take this minus I1 R1 that side, it gives positive. So equation gives I1 R1 is equal to I2 R2. Let it be equation number 3. So this equation we got by applying Kirchhoff's second law for the loop ABDA. So now from the figure, ABDA means this is A, B, D, A. It is the closed loop. For this closed loop, we have applied the KVL. Kirchhoff's voltage law, Kirchhoff's second law. Next, let us apply Kirchhoff's second law for another closed loop. So that another closed loop is B, C, D, B. B, C, D, B is the closed loop. B, C, D, B. We have started from B and we end with B. That is the closed loop. So I have shown here also. Now, for this closed loop, if you apply KVL from B to C, we are moving from B to C in the same direction of electric current. This arrow mark I3. If you take in the same direction of arrow mark, that means we are moving in the direction of current. So the product of IR, that is I3 into R3, that is negative. In the same direction we move means it is negative. So minus I3 R3. So that is minus I3 R3. Here we have written for BCDB loop minus I3 R3 is the first term. Next, after B to C, next C to D. While we are moving in the direction of C to D, see the arrow mark is D to C. We are moving C to D, that is in the opposite direction of electric current from C to D means. When we are moving in the opposite direction of electric current, the IR product is positive. So that's why we can take here plus I4 R4, plus I4 R4. That's why it is we have written plus I4 R4. Next, so if you want to complete the closed loop, we have to move from D to B. When we are moving from D to B, okay, arrow mark is opposite direction. So this is the current direction, but we are moving D to B in the opposite direction. Opposite direction means, okay, the IR product is positive. So that means IR means IG into G. G is the resistance here. IGG, we can take plus IGG is equal to 0. That means here plus IGG is equal to 0. Now total equation gives C. Here minus I3R3 from here to here plus I4R4 plus from here to here plus IGG, that is equal to 0. This is the equation we got by applying Kirchhoff's second law for the loop BCDB. Now, so when the network is balanced, the current through the galvanometer is equal to 0. So when IG is equal to 0, this term becomes 0. Then we left with minus I3R3 plus I4R4, that is equal to 0. Now, so if you take this minus I3R3, if you separate the terms, then it gives I3R3 is equal to I4R4. Let it be equation number 4. We got equation number 3 here, that is I1R1 is equal to I2R2. Equation number 4 is I3R3 is equal to I4R4. Now let us divide the two equations, that is equation number 3 over equation number 4. So equation number 3 means I1R1 left hand side, I1R1 divided by I3R3 left hand side, I1R1 divided by I3R3 is equal to right hand side, if you divide I2R2 by I4R4, I2R2 by I4R4. Okay, so this is once if we divide the third equation and fourth equations, we got this equation. Already we have got the first equation and second equations. From the first equation we have I1 is equal to I3. From the second equation we have I2 is equal to I4. So now here from the first equation, second equations we have I1 is equal to I3, I2 is equal to I4. That means in place of I3 we can write I1. In place of I4 we can write I2 because both are equal. That means here if you write I3 I1, I4 I2, here numerator and denominator I1 get cancelled, here I2 get cancelled. After cancellation we left with R1 by R3 is equal to R2 by R4. This is the balancing condition of Wheatstone's bridge. So R1 by R3 is equal to R2 by R4. That means R1 by R3. So this is the galvanometer arm, either side of the galvanometer arm, that is R1 by R1 is this side of galvanometer, R3 is another side of the galvanometer. So R1 by R3 is equal to R2 by R4. R2 by R4. So now when this satisfies, when R1 by R3 is equal to R2 by R4, then the bridge is balanced. That is, the current through the galvanometer becomes 0. Then the bridge is said to be balanced. For example, if we have R1 is equal to, so 2 ohms, R3 is equal to 4 ohms. That means R1 by R3 becomes 2 by 4 means 1 by 2 ohm. Here, for example, if it is R2 is equal to 3 ohm, R4 is equal to 6 ohm. 3 by 6 gives, it is also 1 by 2 ohm. If both are equal, R1 by R3 is equal to R2 by R4, then the bridge is said to be balanced. Now, this is the balancing condition of Wheatstone's bridge. So, when the bridge is balanced, the current through the galvanometer is 0. This is about it. This is about the Wheatstone's network and balancing condition.